Hello, and thank you everyone for coming to this session. So, before we start, we will proceed with a small experiment on Jeremy. So, Jeremy, as a C++ developer, and just glancing at this code, how would you feel about maintaining it?
Well, not so much, in fact.
So that's a no. We'll repeat the experiment with a different code now. So, Jeremy, how would you feel about maintaining this code?
Yes, much more readable. It looks like an HTTP routing API, so yes, more clear.
So that's a yes. So we can close the experiment now. 100% of the test subjects preferred the second code. So this is a success. In fact, both the two examples we showed, they do exactly the same thing. And our goal today will be to describe to you the approach that we used, inspired from functional programming, to get to this.
And we also will provide you some takeaway that we, C++ developer, can use to apply this approach in other contexts. So, quick word about us. So this is Jeremy, working at Murex for almost 10 years now, and he was there last CppCon for the CDBC poster. And this is Quentin, C++ developer at Murex too, and functional programmer enthusiast. So, what is the context? At Murex, we have some C++ code line, and we have to expose some part of the code over HTTP API. So, the purpose of today is to build over an HTTP transport a layer of code which transforms HTTP requests to response by calling the right code.
So we'll start by doing everything manually. We will build this layer that transforms requests into responses manually, just to show you the concept behind HTTP routing, and also to show you how quickly it breaks when we try to do it by hand. So we'll start with a simple HTTP server, and what we'll do is we will send requests to this server, and the first request will be a GET request to the URI /v1/foo's, and we expect the server to answer with the list of all the foo's inside the system.
So, for this simple purpose, we can start with a simple functions process, which take a request and return a response. Inside the function, we look at the URI inside the request, and we match exactly what we expect. And then we can just return the response by calling the right code with the correct status.
So, this is the resulting code. For just a simple request like this, well, it's readable. So let's try something a bit more complex, and first we will add a second route.
For second URI, you can just add a new if, or you can use a more advanced C++ feature like map from string, the URI, to a function, the function you want to call.
So copy-paste is always the answer, apparently, so it works. We'll try a thing a bit more complex. So what we will do now is, instead of sending static URI, meaning a URI that doesn't contain variable, we are going to send a URI which contains something that we must extract. So for instance, we're going to send the GET request to the URI /v1/foo's /2, where 2 stands for the identifier of the foo that we would like to retrieve. So how can you do that?
So this time we can use exact match anymore. So we have to express all the URI you have to match. And in C++, we have regex, which permit to express this kind of things. So let's use regex and match and from what we match, we know what to do, the global call or the more specific one.
So this is the full code. we can see that it starts to smell a bit. We have regex, we have a bit of extraction, but yeah, it's still readable. We can still maintain it, sort of, so let's make things a bit more complex still. This time, we will send a post request. Until now, we've been only querying, but it's not very useful if we are not able to insert something inside the system first. So we'll send the post request to the URI /v1/foods with a payload. And the payload is the foo that we would like to insert. And then, obviously, if we query for this new foo, we want to get it back.
So this time, in addition of the regex, we have also to match the HTTP, the request method, the HTTP verb, and start to parse.
Yeah, I think we can stop there. I think we reached the point where it's broken already. Let's look at numbers. We just have 4 routes to serve, and we already have 30 lines of code, and 8 conditional branching, and 3 nested levels of indentation. So this is a mess. We started from an architecture which was pretty simple, where we were supposed to transform requests into responses, and we ended up with this, which is a mess, in which we have parsing, matching, error handling, some business code. Yeah, I think we are missing something.
Yes, what we are missing is an abstraction for the routing part. So, as we saw, the manual routing only works for very few routes, and it's not scalable. So, we will explore several approaches. The first one that we are going to look at is an approach that is inspired from Java and C#, and which is called aspect-oriented programming, which we will abbreviate AOP starting from now. So, it works in Java, it works in C#, so why not for us? So to understand how it works, we will go back to the first code that we wrote. We had a process function which took a request and returns a response, and then we started to do the routing inside it. So we want to get rid of this, so we will try a new strategy, which is to split this function and have one function for each of the routes that we want to serve. So basically, we want to get rid of the if statement from the function, have functions which are well named, and find a way to associate a URI with a function that will answer the request. So, as we say, we don't want general purpose function to handle all the requests. So, one function for each different request. And we declare with attributes or annotation the URI we want to match. Something very more declarative.
So this works, it's more declarative, and we can associate that way a URI with a function that will respond appropriately. Now we will enhance it, for instance, to extract some parameters out of the URI. So in our case, we're going to associate v1/foo/ a placeholder named ID. And the framework that we're going to build is able to match this ID by name to the parameter of the function. And to help the framework a bit, we're going to use a new annotation, a new attribute named passVariable. And what the framework will do is when it receives a request, it extracts it, it tries to match it with the right type, and if it's not the same type, let's throw an exception. Okay, now we have several mappings, which can call them routes, and we have to bring them together. Usually in AOP world, it's managed by a class named a controller. So let's reuse these patterns and introduce a controller. And now the framework has the ability to register the routes inside its own engine to dispatch the correct URI to the right functions. And we also reuse the annotations to declare this class as a controller. So I think it works. We can make it still better by using something like meta class. Why not? So we use a meta class controller to declare our foo controller, but there's something that annoys me a bit with this approach. As Jeremy said, we gave the control of the instantiation of the foo controller to the framework. So we cannot instantiate it. We cannot give something to the constructor of this controller. So if my foo and my foo by ID need something like a DB connection, I cannot inject it inside the foo controller directly. So how do I do?
In fact, to get some control back, you have to use some interfaces. So you have to declare your outside world, your dependencies, behind interfaces, which is foo services here. This way, we can delegate to someone the retrieval of the real instance to manage this kind of external dependencies. As we already totally delegate the management of the foo controller to a framework, we also can delegate the way to retrieve these informations by using the new annotation inject, which tells the framework to use some kind of dependency injection to retrieve the real instance.
So that works. We now have 4 different kinds of annotation, but hey, it's chaos. So we can try to instantiate more services. For instance, if we want to deal with the foo in our system, we keep the foo controller, and then we can add a bar controller if we want to deal with the bar of the system. And then the framework is going to do some magic, and it's going to bring the foo controller together so that it dispatches the right request to the right controller. So it seems to work, and I have a question for you.
Yes?
How would you like to implement this?
To implement this, I think this can be fun, a very good challenge.
So a good challenge. Second question, how would you feel about using it if you're not the implementer?
Well, not so, in fact.
Not so much.
Yes. Yes, in fact, we are dealing with things we are not very C++. This code doesn't feel very C++ like we like. We use annotations, so a lot of runtime reflection, and this is doable, but only with some toolings and code generation, so it's fragile and not very natural. We use interfaces, so runtime polymorphism. We use it in C++, but we also like to pay for what we use. So make this kind of things mandatory for every external dependency is not natural either. And finally, we use dependency injection to know the code is correct only at runtime. This is very trial and error process. And this does not feel very C++. We like to rely on your compiler.
So these are only some of the reasons why it's not a good idea already to take just what exists in Java world and put it into C++. But in fact, there are other things that we would like to improve about this approach. So the first thing would be the limited composition. We declared the URI inside request mapping annotations, which means that the URI are strings that are not accessible as first-class elements. We cannot just manipulate them. We cannot create a function that will return them and put them in the annotation, and that deprives us of being able to factorize the URI, for example. So that's the first problem. We have a second problem, which is that the cohesion is pretty limited. We sprinkled some URI in different controllers, in different methods, and so nowhere we have a way to see the router and all the routes that we have inside our server. So we would like to improve on this as well. And the biggest problem actually is the coupling. We put annotations everywhere, and these annotations, they point back to the framework. So each and every line of code that we write needs the framework to work. So we end up with a situation which is pretty much depicted by Joe Armstrong, the creator of Erlang, which describes the situation in which we want a banana, but in fact what we get is a gorilla that holds the banana, and the gorilla is so much attached to the jungle that in fact we get all the jungle. In our case, that would be this. We just want a root, for instance, to test it, and the root is inside the controller and needs the controller to be able to do its stuff. And this controller has also annotation to the framework, so in fact we cannot test a root without the framework.
So, to summarize a little, we want to keep the same level of abstraction to be scalable. But in addition, we want to have code very more natural in C++, so very more C++-like. We also want to increase the transparency and to prefer composition to build higher level concern. And finally, we also want to have building blocks which are reusable without the whole framework.
So, we tried an approach. It did not work very well. So we'll try a second one. This time we'll turn to functional programming, and the way we're going to do it is we are going to look at some of the big ideas that we're going to use, 3 big ideas, and then we're going to show you how we use them to improve the API and get the code that we showed you in the first slide. So, first idea. The first idea is defining clear semantics. We really would like to avoid things like publishing a concept named REST controller, which, quite frankly, does not mean much. So, we will try really hard that every of our concepts that we expose in our API have one abstract definition. And by abstract, we don't mean vague, we mean precise. We want to define something that points right to the essence of the concept that we expose and gets rid of all the implementation details that we don't care about. The way we're going to do this, we're going to use a simple trick from functional programming. We're going to use pure function. So for each concept, we are going to associate a pure function that represents the meaning of this concept. So that's the first idea. The second idea is composition. We really would like to avoid the phenomenon that we had before, which is the gorilla banana syndrome. So we'll try really hard again to translate each of our concepts into one separate entity in the code. We don't mix them together inside a class. They are separate. Obviously, at some point, we will have to build the router. So we'll have to find ways to combine them, and the way we're going to do this is by composition. We want to keep really simple building blocks, and then, via the combinatorial power of composition, we want to find ways to assemble them together in many different ways. Third idea is to keep and to use simple constructs. So at some point, we have to take our concept and put them into code. When we're going to do this, we are going to always try to go down the pyramid. So we're going to use plain old data, and by plain old data, we mean data without behavior. Something like a vector could be qualified as plain old data in our definition. And if it doesn't fit, well, we'll try functions. If data and function don't fit, we try classes. And then we're going to go to metaprogramming and things like this for the icing on the cake, just to make things look nice. So that's the approach.
So, a quick summary of the goals. We want to give meanings to the exposed concepts. We want to focus on composition, so to use things which compose well. And we want to prefer simple constructs to facilitate the composition. So, in our domain, this leads us to 4 main concepts and 1 sidecar. Let's start with the simplest one, the handlers. The handler is here to make the glue between the outside world, the HTTP world, and the business logic. He has to, for a specific request, take parameters from the URI and return the appropriate answer. Applied to C++, this is just a simple function with the request and additional parameter, and return the response as output by, of course, calling the right business code. We don't need any interfaces nor dependency injection of any sort, just a simple function.
So that's the first concept. Now we're going to look at the second concept, which is the one of a path. So what's a path? It's something that, if we match it, we want to execute the associated handler. So we could see it as the set of accepted URI for a given handler, which can be seen again as a function from a URI to a Boolean, which says if it's inside the set. And that would work. But we would like to refine it a bit. Because if we look at something like a regex, we can see that there are capture groups. And so, in our case as well, we would like to extract some things from the URI and give it to the handler if it matches. So if we do this, we're going to refine our concept to extract the parameters and their types. And that gives us the definition of a path, which is a function from a URI to an optional tuple of parameter. Why is it optional? Because we may not match. So that's the semantic model. How would you translate it into code?
Into code, we choose to not have a direct mapping from the semantic model to the code, but to keep only data. The transformation URI to parameters doesn't appear here. Indeed, we have only the static definitions. But the key point is to store enough information to be able to fulfill the semantic model when we really need it, so at runtime. It is also possible to notice we can construct the path piece by piece. This way we can build a partial path, which is a valid path, and reuse it to build another one. So, very composable. We just talked about combining things, and we already defined two concepts. Now we can take a look about how we can have a relation between them, and this will lead us to the root concepts. But instead of presenting it directly, we will do the exercise to rediscover it from the semantics model of the previous one.
So let's do this. We have a path and we have a handler. We know that they are associated to each other by the very definition of a path, which is if we match it, we want to execute the associated handler. How can we find the semantic model of a root? Well, we are going to look at the semantic model of the path and the request, and we are going to try to match them and see what we get. So the path was a function from a URI to an optional tuple of parameter. And the request was a function which takes a request, then a tuple of parameter, and returns a response. To match them, we're going to transform these two equations, basically, to fuse them into one. So, the URI is inside the request. So we can transform the first function and says that, in fact, we're going to take a request and return an optional tuple of parameter. Now, we see that we have the request in the two functions, so we can try to factorize this. We can always do this thanks to currying, which is the fact that when we have a function with n arguments, it can be seen as a function which takes only one argument and returns another function which takes n minus 1 arguments. So we can factorize things like this. Now, if we look inside the parents, we see that we have an optional tuple of parameter, and we would like to feed it inside a function which takes a tuple of parameter, which is not optional. But we can fix this. We can just put optional in the input and the output of the second function, which we can do, again, thanks to functional programming. The name of the concept is functor. And now we can fuse these two functions by composing them, and what we get is the concept of a root, which is something which takes a request and returns an optional response. So that's the semantic model.
This is the semantic model of the root, but we just have to refine it a little about the needs behind these definitions. We also need to match the HTTP verb. So a root needs to match the HTTP verb, the URI against the path, and to call the handlers. In C++, we choose to use the HTTP verb as constructor and to bind the path with the handler. The semantic model of the path returns some parameters, so we are able to match them at compile time with the signature of the handlers.
Okay, so one thing to notice is that we are able to keep the types. So if we want to capture an integer and the function that we provide accepts a string, for instance, it won't compile. So this is how we get a route. Now, one of the problems that we had before in the AOP approach was that the router did not exist. We couldn't see it. We were assembling controller and somehow, something was dispatching the request. We would like to have things that are explicit, so we're going to build a router. So what's a router? Is something which takes several routes, and it will take a request, and it has to return a response. Even if no route match, we have at least to return something like 404, no resource found. So the definition is this simple function. How can we do this into code?
Into code, we choose a simple function which takes a variadic number of routes, and behind it will permit to dispatch the request to the right route, the right business code to call. As Quentin said, we have a default route. We ask to, like a switch, a default case in a switch, to return resource not found if nothing match. So this is very concise. With these 8 lines, we describe all the previous manual attempts we saw just before.
So we are done with the core concept of the API. So we've got the handler, the path, the router, and the route. And now we will describe the last concept, which is not strictly needed, but which is really useful. It's the concept of a middleware. To explain what a middleware is, we first have to explain what are cross-cutting concerns inside the server. So here are 2 routes. We have a first route which lists the foods of the system. And we have a second route which lists all the bars of the system and returns them as response. Actually, inside the HTTP server, we might need something more. We might be interested, for instance, to log every time the first route is matched, because it's so important. The second route might be very critical, and we might be interested in adding some additional write checks on top of it. And the way we could do this is I could go inside the list all foo function and just add some logs. And I could go into the list all bars function and just add some additional write checks. But it would not be great in terms of design.
Indeed. It is possible to do better, or we think we do better. So the purpose of the middleware is to provide decorated handlers. So a middleware is just a function which takes an handler and return a new handler decorated with the new behavior. In your Lloyd case, This will be a simple function which returns a lambda, and this lambda calls the previous handler, the original one, and do the special stuff here to log the URI. Very simple.
So a middleware is just a function which takes a handler and returns a new handler, decorated with some new behavior. And this is nice because we return the same thing that goes inside the function. So we can take a handler, decorate it, and it returns a new handler, which we can feed into a new middleware, which gonna returns a new handler. So we can compose them. Which means that we can build something like a standard middleware by composing something that first checks the rights, and then if the rights are granted, logs that we have matched the request, and then we'll call the appropriate function. So using this simple trick, what we can do is just rely on composition to define only simple building blocks. With rights will be a very short function, with logs as well, and offer some ways to combine them so that the user can have plenty of behaviors available out of really simple building blocks.
Now we have defined your concept and the APIs, we can take a look at the result and some benefits we get from this usage. We transferred the 4 requests and here's the resulting code, the full resulting code. We'll come back several times on it, so let's start with some numbers. We have 4 routes, 29 lines of codes, which is quite similar, but it seems more scalable in this case. The cyclomatic complexity is very low, 1, and we think we are at a good level of abstraction.
Now, if we go back to the code, we can look at the shape of the code and see that it's split in two, basically. So we have the left part, which is the router, and we have the right part in which we put all the handlers. If we zoom on the router, this is what we get. So it's concise, it's pretty readable, and it defines all the routes that we have inside our server. This is how we get the cohesion. So another cool trick with this server is that it's totally decoupled from the transport layer. So what you can do is just take this router, it behaves like a function, you can feed it a request and see what goes out. So we can test it easily, without mocking, without dependency injection. We can even do better. We can zoom on just one route and assign it to an auto variable, for instance. And then we can test this route in isolation. So we can just try our list all foo and see that it extracts the variable correctly from the path, for instance.
The other part are the handlers, and finally they are just simple functions. They are not coupled together behind an interface. Each of them are so simple, we can use them and test them independently without dependency injection of any sort. As a result, we think the client code is very simplified. It's very easy to reason about it. Each piece or concept are understandable in iterations. So the amount of knowledge to use this kind of API is very low. And this transposed to the client code too. We enforce the client code to build it in iteration in the same way. So very easy to combine.
So one of the reasons why we think that it's simpler to use this API is because instead of going the AOP road and going up the layers, inside the AOP approach, we used mainly annotations, metaprogramming things, and so on. We went down, and we don't use powerful constructs, which are often complex. Instead, we use really simple things, like data and functions, which are really composable. Functions, to compose them, you just have to match the types. Data, to compose them, it's really easy. You just nest the data inside another data. But in fact, there is another advantage in doing this. Because when we go up the layers, what we get is really often opaque and hidden. Metaprogramming things, they happen during the compilation, so at runtime you cannot even see them. Classes, you build them mainly, for instance, for encapsulation, so you cannot see inside them, which is good for implementation details, but for some things you want to show them. By going down the pyramid, what we get is plain old data, for instance, and plain old data, you can inspect it, you can look at it, you can transform it. And this allows us to get dry. So what is dry? It's an abbreviation for do not repeat yourself. And it's often misunderstood as something which is about code duplication, about copy-paste, basically. So this is a quote from Dave Thomas, one of the guys who coined the dry term, which says otherwise. He says that it's not about copy-paste. It's not about code duplication. What it is about, it's about knowledge. There is a ton of knowledge inside the application, and what we want to do is try to put this knowledge in one place, for each piece of knowledge, to have one place, which is the authoritative place, from which we can derive the other piece of data, from which we can transform the data to get the same knowledge under a different form. So that's the principle of dry, and in our case, it would translate into what?
In your case, dry is about keeping one referential of information. So in your specific domain, this is a router. We have so much information inside the router, it would be a shame to not use it as the referential. We also choose the code because we are C++ developer and we like to rely on the compiler. But this is not the point to choose code. The key point is to choose one referential. It can be the code or some resource file, XML, YAML file, anything you want, but to derive this information to other forms.
So, one first example in which we use this information, we already showed you. It was type safety. We use the router to contain data, and types are a kind of data. And what we did is we avoided to erase this data. So we keep the data, we don't erase the types. And because we do this, we can match it against the handler and check that these are the same types. And again, if they don't align, we don't compile.
We can reuse information inside the router to, for example, generate documentation. We have all the information. So for a given router, we are able to visit it and to generate for each of its routes some kind of documentation. I think you like random stuff.
Yeah. So by visiting the information, we can generate documentation, but we can also do other things. One of the things that we found really useful was random generation. So what do we mean by that, and why would it be useful? So here we have a sample code in which we have a router with two routes, and what we can do is implement pretty simply a generate function, ask to generate two random routes, and feed them back into the API. If we do that, we are able to do something like fuzz testing, for instance. We can check that our router will accept all the routes which should be accepted. So that's one use case. There is a second use case that we found. We could, for instance, have a client which is interested in testing our HTTP server and will ask us for sample routes so that he can test against us. Again, we can just ask the generate function to produce some routes. We can even ask this on single routes so that we can generate a route, send them inside the mail, I don't know, to the client so that he can test the API. So these are only 3 use cases that we found, and in fact, there could be plenty more.
In truth, we can't predict the usage of our API. So, by keeping the information open, we allow the user to exploit the information he gave us to do things we can't anticipate. We don't think this will violate the encapsulation principle. It's just re-exploiting information he already provides.
So basically, what we want to say by fulfilling dry and following dry is that there are really 2 ways to look at this code. One way to look at this code would be as a piece of code that dispatch requests to the associated handlers, the appropriate one. The second way we can look at this code is as something which is responsible for the information that we give it. When we start seeing this code as responsible for the data, we know that we can reuse this data, and we know that we should do the best we can not to lose this information. So no type erasure, for instance, not to hide it. It's useless to encapsulate information that was provided to us by the client, and to make it available so that the client can reuse this information that he already gave us to produce additional features, build some tools, for instance. So, with that, we presented basically the API and what it looks like, and we would like to give you some takeaways that we think can be transposed and used in other contexts.
So, the first one is to define the concepts. Very abstract, but very precise. And of course, apply to your domain. Think them as pure functions. They do one thing, but one thing well. And don't let the code disturb you. Think very high level, then, in a second time, try to apply it to the code. And finally, C++ concept and contracts will help us a lot in the future.
The second big idea that we think that we can apply almost everywhere is composition, basically. One of the key principles of functional programming is trying to have separate blocks. So we try to keep our concepts separate, and then we find ways to compose them. Composition allows us to build complex behavior out of really simple building blocks. And to do so, it's much easier if you're using simple constructs, like data or functions.
And finally, leverage on the information. So keep them and allow to transform them. Make the information open by using some plain old data, and what the user gives you is very precious. So keep them safe. And APIs are responsible for the given data. Finally, use this information everywhere you can.
So, these are only 3 big ideas of functional programming. There are plenty more that you can take and reuse. But we would like to step back and look at what we did today. The first thing that we tried was taking something that exists inside another language and just transpose it blindly. So we took AOP, we look at annotation, transform them into attributes, and yeah, it did not work out very well.
In the second times, we did not attempt to copy feature. We just adapt ideas, and it's worked much better.
So basically, we think that there is a lot of things that are attractive in functional programming, and maybe we would like just copy the features. But maybe the best way is just to, instead of looking at the features, looking behind these features, looking at the motivation, the big ideas that are behind these features, and in the end, just steal the ideas, not the features. So, thank you. So if you have some questions. Sorry?
That email? That's not email.
No, that's Twitter handle.
Twitter. So is this framework that we can use?
You mean is it available on a GitHub? No, not yet. No.
We are working on it internally in our company, but it's not released yet.
Did you try to apply the same approach for asynchronous handlers, for instance, with BoostHCR?
Not really. This approach, we used it in different contexts. I had the last assignment about a logging API. I could use the same. We think that you should be able to transpose it in really different contexts, but yeah, we are just experimenting with it. So.
I saw the example, the parameter. Now, just support one parameter. If we have more parameters, how to write it?
Sorry, I didn't get it.
I saw the example, the request, the GET request.
Yeah.
If we have more than one parameters.
Yeah.
For example, we have integer or string or double, how to write the code.
Okay, so the question is, what if we have several parameters? We can, in fact, the way we, maybe we could go back to the slides where we have some path. What we provide inside the API is basic building blocks. So basically, you saw that we have a parameter path to say, for example, that we want to match an integer. We have another one for stud string, but you can define your own, and you can combine them with the slash. So you can do, for instance, all slash parameter stud string slash param int slash user slash and so on. So you can compose this, and what's going to happen is that if you define a route with this path, the handler has to accept as many arguments as there are elements that captures elements inside the URI. So basically, if you have a lambda, for instance, the lambda will take, and if you have param int, param stud string, the lambda will have to accept a request followed by an integer followed by a stud string.
Okay. Another question. I think maybe it can be improved. I think that the parameter and the body can be eliminated because the path is fixed, right? And the input parameter can be deduced by the handler's parameters.
Yeah, maybe by changing. So the question was, maybe we could remove some of the type information inside the path so that, in fact, we can try to deduce them from the handler. I think we could do that if we just are interested inside by the dispatch of the request inside the route. But what we build with the path is that we put them inside the router, and we can reuse the information at every level. So we can reuse the information of a path and ask the path, can you please describe yourself? Or can you please generate a route that would match the path? So maybe, yeah, that's a trade-off. I mean, trying to have components that are independent and which can work in autonomy makes a bit of redundant information, maybe. Yeah.
Thank you.
Some other question?
What requirements do you have for type
typical S parameter?
So, do you want to take the question?
In fact, not so much. Primitives are handled very easily, but if you have, you can provide serialization adapters by using some kind of ADL. This can be our specialization. It can be every kind of types.
What we do basically is that we ask for functions to be available on a type. So we already provide some function to describe, for instance, an integer to indicate what is the pattern that must be matched inside the URI. And the same for generation. So some kind of arbitrary generator, so available on an integer. If you define these for your types, then you can just put this inside the API and it will work fine.
How do you hold different types of functions in the router type?
Sorry, couldn't hear it.
So how do you hold different type of functions in the router type?
Okay, so the way we do it is we don't erase the information and we use boost ANA. So,
thanks.
But you could use different things to. I mean, you could re-implement something to visit heterogeneous sequences. That would work as well.
Okay, so I'd like to know what is the actual type of that router? Because I saw auto.
Yeah.
What is that type?
It's ugly.
So it's big. It's everything. It's
yeah,
everything
it's big.
That's in the list.
And that was a question that we had in a previous session in which it was asked how big it would be and if it would not break. In fact, what we can do if we go to the router is that since the router accepts a lambda, we can, inside the lambda, put another router if we want to erase types. If we do that, we lose some of the features because it becomes opaque, basically. But it allows us to, for instance, declare a router specialized for the bars, another one for the foo's, and bring them together as a router for the whole HTTP server. But basically, it's more meant for small services. But yeah, the type is a router underscore T, templated on the path, templated on, yeah, you get it.
I got it. So one more question. So when we check a request, it goes in order.
Yeah.
So that means that the first route is always tested. So routes towards the end might take a little longer to match? Okay.
That's one strategy, but...
It's one strategy, but in fact we have all the information, so we can build more advanced way to reorganize the matching using a tree or a hash or everything we want, in fact.
In fact, there are some APIs that we looked at in Clojure and Haskell languages, and they sometimes offer different ways to match. So some of them, if they find out that all the routes are static, they just build the map, because it's the most efficient way. Some other API, they try a try, so the common parts, and it goes down. It really depends.
So you can have like partial matching, and then you can have a new router that goes through, and then your describe API and everything else will work through that. Because you still have matching because the router matches, right? So you can have that on the path description.
So just to rephrase, because I'm not sure to understand, you mean that we could put a router inside the router, or?
Yeah, you put a different router within inside the router, but using the path syntax. So you have foods, param, and then you have a new router in there.
Yeah, maybe. So the...
Say for example, you've got your version and your thing and your other stuff, you don't have to be matching against that every single time because it succeeds and it pulls through to the other one. And that does that look?
Yeah, I guess we didn't try this, actually, so we didn't think about this. Yeah, the remark was that we could maybe improve the syntax of the path to, for instance, put a router after a slash. Yeah, great solution. We didn't thought about that. Some other questions? Or? Okay, so thank you.